where we were in last class. So we were working on this game of Pig. We saw the number file video of 2-player Pig, which is how you're supposed to play Pig. But we're doing the simple 1-player version first. We're going to build up to the 2-player version. And in the 1-player version, it was like this. Let's make a new note. So in the 1-player version, basically, you roll the dice. You decide, do you want to roll again or stop? So your actions are either roll again, or stop. If you stop, you immediately collect whatever the sum of all the dice you've rolled is. If you roll again, then you can add on to your total, but if you roll a 1, you go down to 0 and lose. So the rules are, if you roll a 1, if you roll, let's do it the cool dice way, a 1, then you go bust and you lose, which is just like in blackjack or an easy 21. If you go above 21, you go bust and then you just like lose. But otherwise, if not go bust, your score is the sum of dice. Okay, so you choose how many times you want to roll it, and you can stop at any point. So you see your outcome. You can choose to roll again or stop. If you roll again, you risk going bust, but you also have a chance to get more money. And in this 1-player, 1-round version, your goal is to maximize your expected score. Maximize the expected value of your score. So you can think that you get $1 per point of score you have, and you're just like you're like asking the question, do I want to risk everything I have and risk going bust, or do I want to bank it and just take what I have now? Okay, that's what you want to do. And one of the strategies we came up with last time is this kind of hit below L strategy, which is using the same kind of name as for blackjack. So if you're below some, you predefine some threshold L, and if you're below that, you roll again, and if you're at L or above, you stop. And the question is, if you're going to follow a hit below L strategy, can you figure out what the optimal value is? So which L's are too big? If L is way too big, then you're being very greedy. If L is too small, then you're not being aggressive enough. And here is my little hint. Do 2 calculations and set them to be equal. So calculate the value if you stop at L, and calculate the value if you choose to roll again at L, and compare those 2 values. And I'll say one other thing. I've gone on one real-life job interview in my entire life, and it was at a bank for some like finance thing over a summer, and this is the question they asked me. So I got it right, and then they offered me a lot of money, and then I didn't do the job. So then I think I taught calculus at a little like community college thing. Anyway, yeah, go ahead and do that. I'll give you a few minutes to think about this, and if you do this calculation, you can try to figure out what the optimal value for L is. Okay, I'll give you like 3 minutes. At least we'll see how many people have answered. Oh yeah, the rules. Yeah, I can bring up the rules. Yeah.
It's like 2 a.m.
What's the average? I'm not sure exactly what like the
Okay, there's only like 10 seconds left, but I think I only have 6 answers. Who could use another minute or so? Okay, let me give you another minute, and then we'll take it up. Of course, I will show you how to do it. Let's do 2 minutes. Why not? What's up? Yeah. Oh, I mean, calculate what would happen if you stop at L. Calculate what would happen if you roll again at L. And then compare those values. And that'll somehow reveal what L has. Yeah. Yeah. That one's easy. It's L. If you're at L and you're like, I'm stopping, you get $L. Congratulations. What happens if you roll again? How many dollars do you get if you roll again? Yeah, so figure out what that's some expression. Yeah. Okay, so there's like 30 seconds left. Put in a guess, even if you're not done. I will show you how to do it, so you've had a chance to think about it now. You'll maybe see how things work.
Well, I'm just saying you.
We solve this. This 3.5 is the expected value from each roll, assuming each element. Roll the one. That's the expected gain times the 1
Okay, let's take a look at what people said. The optimal value for L is, all right, 1, 3, 4, 7, 8, 11, 12, 14, 15, 17. This one is too high. If you're at $1,000, do not stop rolling. Stop rolling. Okay. 3 people were in 20, and 20 is the correct answer. But this is good to see that. Good to get the information that people didn't see how this calculation works. I'll show you guys how to do it in some detail now. So how did we get this answer of 20? And I'm gonna use our notation that we kind of developed last time. Okay, if it will come up. Where's my blackboard? It's hidden. I see what's going on. I see. Okay. So let's calculate. And what we're really doing is we're implementing a policy, right? A policy means you decide what you're going to do at every state, and we're using the roll at what I call it, hit below L. Hit below L is what I've been calling it. Hit below L. And so this is a policy. We use the letter pi for policy. And what it says is, if you're at the state S, you're at S. Okay, and I really should specify, you're at S and you're still alive, right? Because last time we saw alive, S is some number. So you're at S dollars and you're still alive, like you're still choosing to roll again or not. Last time we saw that, very technically speaking, if you want this to be a Markov chain or a Markov decision process, the state space is not just one, like the natural numbers, it's the natural numbers plus whether or not you're alive or not. We're going to sort of drop these as we go for convenience, but just to be crystal clear, if you're still choosing whether or not to roll again and you're at S, the hit below L strategy says, what do you do? Well, if you are less than L, then you hit, that is roll again, oh boy. Okay, and you stop if S is greater than or equal to L. Right? So a policy is exactly an assignment of actions to every state. Policy. I suppose you also need to specify what you do when you are done, right? But we know the game ends sort of like as soon as you're done, so we don't actually need to specify what these are. But very strictly speaking, that's how we had it set up last time. This doesn't matter. I'm just going to say it doesn't matter. So we're just going to think about this one. Doesn't matter. Okay, and we're going to calculate the hint was telling you is calculate two things. We had a name for those two things. They are what happens if you're at L, and choose to either roll again or stay. Roll again or stop. This kind of sentence, that's how you would describe it in English. This is the calculation we're going to do. We had a name for this. This is called the Q function. Somebody after class, last class, I was like, what the hell does Q stand for? Someone told me it stands for quality. So we're calculating the quality of rolling again and the quality of stopping, okay? So Q, this is called Q, and it is very technically Q pi, which means that what you're at state S now, and you are going to roll again or stop. Let's do stop first. Or we'll do S comma roll again. And we're going to calculate both of these things. These are the Q values. And then we're going to compare them. And we want to do it at S equals L. So let's do it at S equals L. You'll see that'll make life easier for us. So we're going to put in S equals L. Let's do that, L. So when you're exactly at this like threshold point, the policy says that you should at L stop, right? But the Q function inputs what are you going to do exactly now, and it could be anything, right? So there's no, like this Q roll again with a pi makes perfect sense, even though the policy says stop. We're overriding it, we're saying no, right now you are choosing to roll again. That's what the Q function does. So this is the Q function, and it's what's going to happen if you choose to roll again or stop. One of these is very easy. What happens if you choose to stop? So you're at L, you choose to stop, you get L dollars, right? You just stop the game, great, good for you, you got L dollars. That one is very simple. What happens if you choose to roll again? And so what this one is let's write it out. This means you are going to, the expected value of your total return, given S0 equals L. So you start at position L, and you choose to roll again. So A0 equals roll again. Let's make that a fun color too. Roll again. Okay. And in this situation, you're going to follow the policy pi everywhere after. So you're going to roll again now, and then after you roll again, we're going to follow the policy pi everywhere after that. And I'll tell you what will happen. If you roll again, there are 6 things that can happen, right? Let's just write out the 6 things. To calculate the expected value, we'll add up the 6 things that can happen times the probabilities. The probabilities are all 1/6. So rolling again, a 1/6 chance, you roll a 1, and if you roll a 1, you're going to leave the game with $0. So there's a 1/6 chance of 0 because you roll a 1. Roll a 1 and lose. So if you choose to roll again, there's a 1/6 chance you get nothing. But there is a 1/6 chance you move to the position L plus 2. Right? If you roll a 2, you go up to L plus 2. And if you go up to L plus 2, what will happen? Well, then the amount of what will you get? You'll have the total return starting at L plus 2. So let me write that actually. I'm going to write it out kind of long form. Total return. And you'll have S0 equals L plus 2. Let's do plus 2, and that's because we're saying you roll a 2. Roll a 2. And this is the nice thing about Markov chains, is that where we came from, right? We started at L and we chose to roll again. None of that matters. The only thing that matters, once you've rolled a 2, now you're at L plus 2. And we're going to keep going from there. And you can add this up. It goes all the way. There's going to be a bunch of terms like this. The last one will be the same thing. Of the total return given S0 equals L plus 6. That's a thing that can happen if you roll a 6. Plus 6. Okay. And that's if you roll a 6. Okay, and I skipped over 3, 4, 5 just to save a little space on our page. Okay. Clear so far? Okay. This horrible expression, which was super long, we actually have a nice name for it. This thing has a name. That's the value function v. So I could have saved some space by just writing out this is equal to 1 over 6 times 0. That's 0. I'm not going to write that anymore. But it's 1/6, and then you have v pi. So that means the value function under the policy pi. So you're going to follow the policy pi starting at L plus 2. L plus 2. And we're going to have all the way up to 1 over 6 v pi of L plus 6. Okay, great. So the Q function is some combination of these v functions, right? What the value you get if you choose to roll again is related to the value you get at states L plus 2 to L plus 6. And the value function, we don't know what it is. Like if we knew what it is, we would be quite happy. Like in particular, what is the value function at 0? That's like how much would you pay to play the game? Like we don't know that. But we do know the value function at these special states, L plus 2 to L plus 6. And that's because the policy pi is not just any policy. Remember, pi is the hit below L. Hit below L policy. So it's not just some arbitrary policy, it's the special hit below L policy. And so I'm going to be able to simplify these v's away. Does anyone know what would it say, for example, v pi of L plus 2? What is that? So v pi of L plus 2 says what is the value of starting at position L plus 2 if you follow the hit below L policy? Yeah?
It's L plus 2.
It's L plus 2. Because the hit below L policy says at L plus 2 you would choose to stop. And if you are at L plus 2 and you choose to stop, you get L plus $2. So this is a very nice thing. V pi of S is equal to S for S greater than or equal to L. That is just a fact about this policy. Because it's so simple, this will always be true. And so in our case, this simplifies. This is 1 over 6 L plus 2 plus 2 plus dot 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 plus 1 over 6 L plus 6. Which I guess there's not that many dot dot dot. Sometimes in math they use to hide infinitely many things. We're hiding 3 things. So this is kind of like a laziness on my part. Okay. Okay, this one I can simplify. This is equal to 5 over 6 L, because there's 5 terms. Each of them has a 1/6. And then you do 2 plus 3 plus 4 plus 5 plus 6, all divided by 6. 2 plus 3 plus 4 plus 5 plus 6 is 20. Okay, plus 20 divided by 6. Great, and this was all Q pi of L. And rolling again. Roll again. Okay. Questions or comments about any of those steps where that came from? That is the calculation that I wanted you to do. Maybe there were more steps in there. It's okay if you didn't know how to do it. But that is the value of choosing to roll again. Okay, now we have 2 things to compare. We have the value of rolling again, and we have the value of stopping. And that is for the strategy at L. Maybe let's copy this one out. Q pi of L and stop is equal to L. Okay. So if you're exactly at this threshold L and you choose to roll again, you would get 5 over 6 L plus 20 over 6 in expected value. That would be your expected total return. If you are exactly at L and you follow the strategy and you choose to stop, then you would get L. And now is where you have a little bit of logic. And you just kind of think like a human about how playing this game works. If L is too big, this is how we think. We're trying to find the optimal L. So our goal, find the best L. Find the best L. Some people would call this L star. L star is the best possible value of L. And here is my little human thought bubble. I guess I'll draw a cartoon of myself thinking. All right. So I'm thinking, if L is too big, what would that mean? If you choose an L that is much bigger than the optimal one, then you're kind of being too greedy, right? And when you're too greedy, then you are rolling again when you should stop, right? That's what kind of being too greedy means. And if L is too big, this is too big. I guess this is like a little Goldilocks cartoon over here. So if it's too big, then I think that Q pi of L roll again, you've chosen to roll again, but you should have stopped. So the value you get by rolling again is less than if you had stopped. So if L is too big, then this should happen. So if L is too big, then that should be less than that. If L is too small, then you choose to stop too early, and you should have rolled again. So if too small, okay, I guess this is all inside my my thought bubble. Let me just do it like that. Okay. Then Q pi of L stop is less than q pi of L roll again. So like if you're choosing an L value that's too small, then you are stopping where you should have rolled again. Rolling again would have gotten you more expected value, right? And all of this comes from the human intuition of thinking about like risks and like larger values versus smaller values and how they feel more risky. If that's too big and that's too small, then just right, L star would have the property that q pi of L star stop is equal to q pi of L star roll again. So at the optimal value, these two things are sort of equal. And that's saying like, at first, when you're first playing the game, you start at 0. You're like very excited to roll again. And you're like, yeah, let's roll again. We're going to get more value by rolling again. And then eventually you cross the optimal value. And then you're like, whoa, 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 we got to stop here. Like stopping is the better thing to do. And right in the middle, that is exactly this like neutral point where it switches from one being higher than the other. That is exactly the optimal place. That's the L star we're looking for. Questions or comments about this idea? Okay. And the nice thing is we have a formula for this. Q pi of L star stop is exactly, that was L star. Q pi of L star roll again is 5 over 6 L star plus 20 over 6. And now that's a nice equation you can solve for. Move the 5 over 6 to the other side. 1 over 6 L star equals 20 over 6. And so L star equals 20. Okay. There you go. And this is a nice like argument that the optimal stopping value is 20 in this case. Questions or comments? Okay, a good thing to do. This stuff, you'll notice I was literally waving my hands around. Right? This is not purely rigorous. I think you need, if you wanted to make this rigorous, you would need to bake in some assumptions and things. I think you can make this rigorous eventually. But it's a little bit tricky. But this is a good heuristic way to do it. One thing we can do, because we did a whole thing on Markov chains for the first couple weeks, we can actually calculate v pi of s exactly. Can calculate v pi of s. This is actually very similar to what you guys did on lab 1, right? Once you have fixed the policy pi, right? Once somebody tells you we're going to do hit below L with L equals 17, then you can calculate the value of that state. You can calculate the probability you end up anywhere. You can do all of these things. And then you can calculate v pi exactly. And once you know v pi exactly, we can figure out for every possible L what it is. Right? So this is really v pi L. Pi L is hit below L. Before I didn't label it with the L. And I did that really quickly for you in a little Google Colab. The reason I wanted to show you this is because I am using the hack that they did in Numberphile where they leave off a state. So I'm going to show you how this works. It's a nice little shortcut that you can use sometimes. So now that you guys are experts and know how to do it the real way, you can do it this hacky way, and that's over here. So I'm using a sub-Markov chain. A Markov chain, all the rows sum to 1. In this one, I'm leaving off one state. And so the rows are going to sum to less than 1. That's why I'm going to call it a sub-Markov chain. So I'm going to have a matrix. I'm going to leave off the state. And here is my hit below L sub matrix. So this returns the matrix, but I'm leaving off the state. Maybe I'll write this down. I'll leave off the busted state. So only give probabilities for alive states. So what I'm doing is I'm never keeping track of any of the states where you've busted or chosen to stop. Those states just like are not in here, and so everything's going to sum to less than 1. The first thing I do is I have an n max. This is the largest state I want to keep track of. I set it to L plus 6 because you can never, if you're always choosing to stop at L, you can never get past L plus 6. How would you have gotten to L plus 6? Well, you would have had to been at L minus 1 and then chosen to roll again. I think you can actually only ever get to L plus 5, but it's nice to leave one room of buffer. Then I have this matrix M. This is just like your code, your lab projects. I start off with an n max plus 1 by n max plus 1 matrix, and then I make the entries by this kind of pattern that we've been following a few times now. The start index is everything from 1 to L, and the dice rolls, this is where you choose to roll again. The dice rolls are 1 to 6. You'll notice you got to be careful with range in Python, if you did range 1 to 6, it would not include 6, but you got to include 6. So I added a little 1 there. If you roll a 1, normally I would say you move into the state where you're busted with probability 1/6, but I'm not keeping track of that here. So I'm just throwing away that probability. That's why I do nothing there. And then I add a 1/6 chance to moving from start to end, where end is where you started plus the dice roll. These are all the roll again states. Over here is all the stop states, so everything from L up to N max, and I just make those 1. So this makes the matrix, and it's not a proper probability matrix because it doesn't sum to 1. Some of the rows only sum up to 5/6. Every time you choose to roll again, it only sums up to 5/6. That extra 1/6 chance is just lost to the ether, and that represents you kind of busting. You can really think about it. I really made the matrix and I forgot a column. I forgot the column that is the busted column. That's where all the probability should go. I'm just not including it because it's kind of annoying. Where do you put it, right? It's not 0 to n. It's like its own separate thing. You could include it, but I'm just leaving it out. Okay, then I made the value function. The value function, which is computing exactly what I wanted, which is v pi L of s. V pi L of s. So how do I compute v pi L of s? First I got the matrix M, and then I made this prize vector, which has np.a range n max plus 1. I saw in some people's code, they did not know this command, so I'll explain what np.a range is. np.a range outputs the numbers 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, all the way up to n max plus 1. So some people did that with a for loop, which is fine, but it's already a built-in command. So the prize vector is just if you're at state 0, you get 0. If you're at state 1, you get 1. If you're at state 2, you get 2. And then all I did is I took a large power of the matrix M and I multiplied it on the right by the prize vector. That is what you guys saw in lab 3, in question 3, rather. In lab 1 on question 3, if you have some final prize at some later time, in this case the time is t max, you can take the matrix M to the power t max and multiply it by the prize vector. That will tell you the expected value of your prize. So if you get $S for being in state S, this thing is what is the expected value after t max steps. And here I set t max to L. In your lab, you probably set it to like 1,000 or something. But if you're playing this pig game, after L rolls, you're either done, you've either busted, or you've chosen to stop, right? Because every time you go up by 2. So after L rolls, you're actually I could probably even make it t max is L divided by 2. So you go up by 2 every time minimum, or you bust. So all of this is kind of like very similar to what you guys did on lab 1. It's not a real probability matrix. I left out one state. That state has a value of 0, so it's not going to affect this. I also calculated the probability that you've busted. You could also figure that out if you were doing the full matrix. You would just have an entry that tells you the probability. But the way I'm doing it is I'm doing the sum of all the entries, and that's the probability you're still alive, right? So if you're in one of the alive states, then you're in one, either 0 or 1 or 2 or 3. P alive sums them all up, and then P busted is 1 minus P alive. And here's what it looks like if you plot it. So, that's not what I wanted. So on the bottom, I've done it for every possible L. So I've just looped through every possible L value from 1 to 40, and I have figured out the expected score. That's starting at 0. And what is the probability you bust, that you lose the game? And you can see it goes up for a while, right? So these L values are too low. You could have made L bigger and done better. And then these L values are too big. You're leaving money on the table by being too greedy. The optimal value is exactly at L equals 20. And some of them are printed out here, maybe. Maybe not. Let's have it print. Let's print one of these. Okay, let's run all. And what is it? I want to print a V list. What does it not like? Nmax is not defined. Well, this is way past where we want to go. Okay, there we go. Okay, let me print. L equals and V list of L. Let's print these as we go so we can look at what it says. Okay, so here's the list, and I'm trying to convince you that L equals 20 is the optimal. So when L equals 19, you get 8.12. When L equals 20, you get 8.14179. And also, when L equals 21, you also get the same number, 8.14179. When L equals 22, you're being too greedy, and you've lost a little bit of value. Now it's 8.12. And you can see that in the picture. You go up, L equals 20 and 21 are tied, and then you go down. So this was like a lab 1 type calculation for the value function v pi using the methods you already saw. So I kind of went over it quickly, but just to connect what we were doing before to what we're doing now. Questions or comments about that? Yeah.
So your value function, does it outputs a vector or a single number?
This is a great point. It outputs a vector, and I am taking the value starting from state 0. So it outputs a whole vector, which is nice. I know the value starting from any state, but when you start the game, you always start at state 0, and so I'm only looking at the 0 entry. This is how much value you have starting at 0. Yeah, great question. Any other questions? Yeah.
The L value, when it's 20 and 21,
Yeah.
the value being equal to the same.
Yes.
Is that expected?
I think this is pretty surprising. I was surprised by this. But I think it has something to do, and I'm not 100% sure, so you can think about it. But yeah, maybe you know?
Well, just when I did it, it was you either, when you're at that spot, you have a 20/6 chance of, well, you have a 50% chance of getting 20/6. You're like expected to either gain 20/6 or you're going to lose 20/6. It was the same either way, whether you roll or stick.
I see.
On what you're expected to win or lose.
Well, that was at L equals 20, it should be the same. At L equals 21, well, okay, remember that if you're in the stop at 21 strategy and you get to 21, you choose to stop.
Oh, right.
So I think it has something to do with,
Is it because you set your, the condition, you put it to +6 and not +5?
so I'm not 100% sure. I think it has something to do with the fact that the minimum roll is 2. So the minimum, like you can never go up by 1, right? So if you, like, there's something about the states 20 and 21 that are the same, and I think it has something to do with the dice being 2 minimum. But yeah, I think that's if you think about it and can come up with a nice explanation, that would be cool. Yeah, it's not obvious to me. I don't think there's a simple like one line, or maybe there is. I just can't think of it. But yeah, it's interesting. It's also interesting in the video. I don't know if you guys watched the rest of that number file video. The person who did the video didn't know this method to calculate things. So they were doing it with Monte Carlo. So they ran 1 million simulations. They're like, wow, look, 20 and 21 are like pretty close, right? But it takes you sort of like infinitely many simulations to realize they're actually equal. So with our method, we got even more accurate. Yeah, it is interesting that they do work out to be equal. Okay. Yeah.
I was just going to ask, is this like we're stopping, are we stopping at L then?
We're hitting below L. So at L, we choose to stop.
Okay, because
Yeah.
I was debating writing like 21 or 20 because when you're at 21, you're not hitting at 21, you're hitting below 21. Does that have something to do with it?
The fact that they're equal?
Yeah, and then if you're at 20, you can also, it's the same chance, so you can also just stay if you're below 20.
Yeah. So I think if you're at 20, then you can choose to roll again or stop, and it should be the same.
But hitting below 20 is the same as hitting below 20.
Yeah, right. So, and if you're at 21, if you chose to roll again at 21, you would lose some value.
Yeah.
So, in the strategy we tried, we chose to stop at 21, and so we got a certain value. If you're at 20 and you choose to stop, that's the same value as choosing to roll again. But the fact that they're equal is still surprising.
Okay.
It's not clear to me that they should be. Like, I could imagine a universe where at the L equals 21 is like slightly higher than the L equals 21 one. I think there must be some coincidence with the numbers or something. And it also, like, when we did this calculation, the fact that it worked out to an integer is also a coincidence, right? Like, you could have baked the numbers so that it wasn't an integer, and then they'd be like, okay, well, L star is 20.1, which means that if you're at L equals 20, you need to choose to roll again. If you're at 21, you choose to stop. So the fact that this is an exact integer might also be related to that. Yeah, it's a good question, fun little mystery. If someone wants to try to figure it out, yeah, do post on CampusWire. Yeah.
Wouldn't it be that because you've made it to state 21, there's no way from state 20 that you could roll again, so having gotten there, then it's the same position because it's not like you can roll from 20 to get to 21, it's the same as...
It might have something to do with that. but state 20 and 21 will be slightly different because like if you add one to an earlier roll, then you could like change the outcomes. But it's possible that there's a way to do it like that. Yeah.
One last question.
Yeah.
So when we land on an integer, wouldn't that mean that it's the same chance of whether you choose to roll again or stick? Wouldn't that be the same chance then? Because we landed on an integer?
Oh, you mean because it ended up being an integer? Yeah, so this is saying at 20, if we had changed the strategy, then the strategy of choosing to stop at 20 and the strategy of choosing to roll again at 20, those both have the same outcome. I guess maybe you're saying that the strategy of roll again... okay, you're right. Okay, we figured it out. There we go. Okay, there we go. So the hit below 21 is the same as stop at 20. Okay, this is why it works. So the strategy hit below 21 is the same exact strategy as stop at 20. And we just proved that stopping at 20, the value of stop at 20 is the same as the value of roll below 20. Okay, so yes, so it's exactly because this L star happened to be an integer. These two things have the same exact value. We calculated both of those essentially. And because they're equal, I think, yeah, I guess this is the part that I missed, is that stopping at 20 is the same thing as hitting below 21. Okay, there you go, we figured it out. Congratulations. Great work, everyone. Other questions or comments? All right, so very nice. It seems like we've solved everything. We're the masters of the universe. And this is the optimal strategy in this game. But in general, what we did will not work. There is a fundamental flaw. So for this simple dice game, it did work. If you're trying to do this exactly what we did for something like chess, there is a problem. And I made that problem into a mathematized question. So you guys tell me what the problem is. So here's what I did. I said, we're only going to go up to some maximum number n. So just like in my code, I stopped at some maximum number, which I guess I set it to be L plus 6, right? The computer can only simulate up to some finite number, maybe 1,000 or something. And my question is, how many possible policies are there that are less than or equal to that number? So only involving numbers up to n, not numbers higher than n. How many possible policies are there? We checked, we did a strategy of doing the hit below L policy, right? But are there other policies out there other than the hit below L policies? So I gave you some options, n squared, n cubed, and 2 to the n. And I want you to choose which of these is like the right size of the number of policies. So think about what possible policies are there and how many are there. I'll give you a minute to think. Okay, there's like 10 seconds left. Some people haven't put in their answers yet, but put in your guess. Just think roughly, like what should it be, right? So going up to say 100, we're not going to look at anything that involves more than 100 points. How many possible policies are there? Is it like 100? Is it like 10,000? Is it like 1,000,000? Or is it like 2 to the 100? 2 to the 100 is like 1 followed by 30 zeros. Okay, let's see what you guys think. All right, 3 people are in n squared, but 14 people have figured out what's going on here, is that there's 2 to the n policies. So like I said, if you're looking at all the policies of things up to size 100, that's like a 1 followed by 30 zeros in a row. So really, 1, 0, 0, 0, a lot of different policies. what I just showed you and what you guys learned on the previous lab is for one given policy, one Markov chain, you can calculate everything, right? But if you wanted to do this for all the possible policies, it is not feasible to do it on your computer. There was a great speed up here. We did like a great hack. We got this really nice plot and we found the thing. How were we able to do that? We did a cheat, which we went down from 2 to the n to n, right? We said, instead of looking at all the possible strategies, let's look at strategies of the form. There is some line, and you do one thing on one side of the line, you do another thing on the other side of the line. And that reduces the number of policies down from exponentially many, 2 to the n, down to just linear. There's only n possible things. So by reducing it down, and that was the very first thing we did, we said we're going to look at the hit below L policy, right? This hit below L policy. By saying let's only look at these hit below L policies, that made it that we could solve it by just pen and paper and just trying things. It could be that the best possible strategy is not a hit below L policy. Maybe you do something for even numbers, something for odd numbers, you do something for large numbers, you do something different for small numbers. So it's not at all clear why this should be optimal. And that really came out in this thinking, right? We had this thinking of too small and too big, and that really relied on kind of like this idea of the amount of risk increasing as you go. The higher you are, the more risk there is. Maybe at some point it switches, right? You like add more to your state and you get less risk. You will actually have to deal with this when you guys do the final project, because in easy 21, you can go bust about going above 21 or go bust below 1. So the middle numbers are different than the high numbers, which are different than the low numbers. The high numbers you can go bust by going over 21. The low numbers you can go bust by going below 0, by getting a negative number. So it's not just like one increasing thing. But by doing this, that's how we were able to solve it. And so now the question is, can we somehow look at all possible strategies? Look at all. And I keep saying strategies. I should say policies. All possible policies. So great. We have a nice solution before, only looking at a very small subset of policies. But we like had our human intuition that told us the best possible policy is somewhere in this small subset. Is there a way to solve this thing and get this hit below 21 strategy by looking at all the possible policies and not like pre-restricting it? And the answer to this question is sometimes yes, sometimes no, but at least there is an equation that needs to be solved. And if you can solve that equation or find a solution to it, that will help you out. And that equation is the Bellman equation. And by the Bellman equation, I mean the grown-up Bellman equation. I guess the last one was the baby Bellman equation. Okay. So I'm going to show you the grown-up Bellman equation. I'm going to show you how you solve it on the computer, and it's going to give back the same answer, which is that you should stop at 20. And here is the grown-up Bellman equation. Let me see. How should I tell you what the grown-up Bellman equation says? Okay, before I tell you the grown-up Bellman equation, I'm gonna write it down on what it says. Let me tell you what the baby Bellman equation says first. This is a reminder, and so you can compare them. Reminder: baby Bellman said V pi equals the rewards plus gamma m pi v pi. This was basically the baby Bellman equation. Okay, what did I do differently? When we were doing the baby Bellman equation, we just had v. There was no v pi. That was because we just had a Markov chain. Someone just gave us the Markov chain. Now we're thinking of Markov decision processes, like you choose the policy pi. But once you have fixed pi, a Markov decision process becomes a Markov chain, right? So once you've pre-decided on the policy you're going to do pi, you just have some value function pi. When you have some value function pi, the baby Bellman equation says the value of the state you're in now, well, you get the rewards now. This was the rewards now. Reward now. Plus, you get the rewards later. And the rewards later, what are they? Well, you take the value function and you move it forward in time by one step by applying the Markov chain matrix. And I wrote it as an m pi because now we have a Markov decision process. If you fix pi, you choose the policy, then you just get some Markov chain. So that's the Baby-Bellman equation, and it had this interpretation of rewards now plus rewards after now. Okay, and this split is the same thing that we're going to do to find the full version of the Bellman equation. So if you can keep this division in mind, that will help you. Okay, so here is the full version of the Bellman equation, and you could write it like this with just v, but I'm going to write it with v and with q, and you're going to see that makes things a little bit easier to understand. So here is the first part, which is to be optimal, you must be optimal now. So you must, to be an optimal policy, you must do two things. And that's why this equation is going to have two parts. So if you're going to make the optimal choices for all time, first you have to make the optimal choice now. Must make optimal choice now. Okay, what does making the optimal choice now mean? It means v pi star, so pi star means the optimal policy, v pi star of s, the value of starting at state s, if you make the optimal policy now, well, I can tell you what it's going to be compared to q pi star of s a. So q pi star of s a means start at state s, take the action a. What is the relationship between the optimal value and the q functions? Well, it's optimal now. So that means choose the best thing you can do now. So it's going to be the maximum over all actions a in a of s. So whenever you have to make a choice, choose the thing that is the best. If you're not choosing the thing that is the best now, then you're not the optimal policy. The optimal policy definitely satisfies this. So this tells me what's the relationship between the value function and the q functions. Okay? The next equation is going to be, you have to make optimal choices for all time in the future. You must make optimal choices. I'm going to say forevermore, because I don't get to say that very much. Forevermore. It's like the opposite of the raven. Okay. What does making good choices forevermore, making optimal choices forevermore mean? Well, whatever you do now, I'm going to call that q pi star of SA. That is the value of the state you're in now, and you're going to take action A, and then we're going to follow the policy pi star forever. And we're going to see that this equation is going to involve v star. And this one's going to look a lot like the Baby-Bellman equation. So I'm going to write this out, and you're going to see what it is. It's the expected value of the total returns given s0 equals s and a0 equals a. That's the definition. And I'm going to do a little bit of slick trickery to write this total returns thing in terms of the Markov chain matrix M and V star. So we're going to see that this is equal to, and I'm going to fill in the steps here, but just to show you the final result. This is going to be equal to R plus what I'm going to call gamma. I'm going to call it MA times V pi star of S. Okay, let me write it as a sum here because I have an S. Sum of S prime, and I'm going to do MA from S to S prime V pi star of S prime. Okay, so that's what the result is going to be. It's going to say that the value you get if you're starting at the state S and you take action A, it's the rewards you get now plus the rewards you get according to the value function V one time step later. And that's because we're going to follow pi star forever. This is a pi star. So you're going to see why that is. But before I show you the proof why, I'm going to scroll up and hopefully I can fit in the Baby-Bellman equation. Okay, maybe I can't fit in the Baby-Bellman equation. But it should remind you a lot of this one. So when there was no actions, the Baby-Bellman equation said V is given in terms of V. And the Baby-Bellman equation tells you that Q is given in terms of V. But we also know that V is given in terms of Q. So with these two equations, you can solve everything. So those two together are what I call the Bellman equations. Very often, if you read a book and they only have one equation, what they do is they combine the two equations to eliminate a variable, right? So for example, instead of writing v pi star, I could have written this. Max, then I would say q equals something something q. That's one version. Another version is they take this q and they feed it into the max there, and then it says v equals max of something something v. Those are both valid ways. So that's the statement of the theorem. I'll prove it in a second, and you'll see the proof is not at all hard. It's this ... It's splitting the total returns into the returns now and the returns later, and using the Markov property. So if you remember sort of how it works, it's not surprising at all. It's a good place to stop for questions on what the statement is saying. Okay, let's do the proof, or at least I'll start the proof. And just like before, the whole trick is to split the total returns, which we had a name for. That was G0. And G0 is the rewards now, plus the rewards in one step, plus the rewards in two steps, and so on, with this discount factor of gamma, so that future rewards count less than current rewards. If gamma equals 1, they all count the same. So that's the total returns. And the nice thing about it is you can write it as the rewards now, and I think I'm off by 1 here. I think this is supposed to start at 1. Let me make it start at 1, so that we're the same as the textbook. Okay, you can write this as the rewards now plus gamma times the rewards, the total return, one step later. So the total return is the rewards now plus gamma times the returns in one step. And so if you have this expected value, q, it splits into two parts. Q pi star of SA will split into two parts. It's the expected value of G0, but G0 is R1 plus gamma G1. So you have these two parts. You have the expected value of R1 given state S0 equals S and action 0 equals A. This is what I'm calling the reward vector. The reward vector R. So this is the rewards now from state S with action A. Then you have the rewards later. Plus, and I'll plot a factor of gamma. So it's just this expected value of G1 given S0 equals S, A0 equals A. Okay, and this is exactly where things are going to get moved ahead in time by the Markov matrix, right? These are the rewards starting at time 1. You are at state 0 now. So I told you you're at state 0 and you're in state S. You've taken action A. This is the reward starting at time 1. Well, how am I going to figure out what this is? I'm going to use the law of total probability to sum over all the possible things that could have happened at time 1. I'm going to sum over all the states. So this last one, this thing, is equal to let's do it in purple. Why not? It's the sum over all the possible things. This is the law of total probability. And it's the sum over all possible states S prime of what could have happened at state S prime. And I'll write it like this. The probability that S1 equals S prime given S0 equals S and A0 equals A. So that's the probability you move to the state S1, and then we're going to multiply by the expected value in that situation. The expected value of G1 given S1 equals S prime, S0 equals S, and A0 equals A. Okay. So just that expected value is a sum of probabilities times these conditional expected values. And now, by the Markov property, conditioning, if you know that S1 is S prime, then it doesn't matter where you came from. S1 is S prime. Once you know that, everything else in the past is completely irrelevant. So this conditioning does nothing. Let's do a dotted line. So extra conditioning is irrelevant. Conditioning is irrelevant. And that's the Markov property by Markov property. So what happened in the past, given the current state we're in, is irrelevant. You might as well just delete it. Okay, this probability is exactly the transition probability, the probability you move to state S prime, given that you're in state S and you take action A. This expected value is exactly the value function V. So this is equal to what I call M for Markov matrix, M of taking action A to go from S prime, from S to S prime, S to S prime, and then this thing is V pi star of S prime, which is exactly the stated result. So there you go. You want to know the expected value one step in the future, you apply the Markov matrix M to V. Okay, that's the proof. All right, it's all very theoretical so far. Let's see how this equation works in action to solve that the game of pig. And we're going to see that it's going to find the optimal solution over the space of all possible solutions, not just the hit below L strategies. Yeah?
You said that you use the law of total probability. Does that
Yeah.
include all the future rewards? Because usually I would expect to see like an M to the T or something.
Yes, yeah, okay, great. This is a fantastic question. So all of the future rewards are baked into G1, right? G1 is the infinite sum, R2 plus R3 plus R4 and so on. So we did this split. G0 was the sum of everything starting at R1. And we split G0 as R1 plus G1. G1 is everything starting at R2. So all the future rewards are already baked in to this term G1 right here. And then when we go to simplify it, all the future rewards are baked into the function V pi star, right? So V pi star of S prime will tell you, if you start in state S prime and you make the correct choices always, how much value will you get? And so this little thing contains all the information about that. So it is really like a clever way of like consolidating the information in the right place to make it like minimally complicated. Like you kind of think of the information about all the rewards in the future as like so complicated. Like what states could we go to? We could go to any states we want, like, but it's all baked into this one function. And so all the information is sort of like brought in to this one thing. So it seems simpler than it is. Yeah. Great question. Any other questions or comments? Okay, let's write down these two equations for our game of pig. So in the game of pig, we have two equations, and because there's always two actions, either roll again or stay, it looks very simple. So it says V pi star of S is the maximum of Q pi star of S stop and Q pi star of S roll again. Roll again, right? And this is kind of how we started earlier, right? We said choosing to stop, choosing to roll again, you can calculate those individually, and by like relating them to each other, you can figure things out. The value is the maximum of both, right? Okay. This one I know, Q pi star of S stop, that one we know. So if you choose to stop, you just get S dollars. So that's very nice. This whole thing is equal to S. What is Q pi star of S roll again? Now this one, in principle, is some complicated thing, right? It's like the value you get if you're at state S, you roll again. But the Bellman equation tells us what it is in terms of V pi. So Q pi star of S roll again. And by the Bellman equation, you just get the kind of thing we saw this morning, which is you get 1/6 V pi star of S plus 2 plus 1/6 V pi star of S plus 3 plus dot 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 plus 1/6 V pi star of S plus 6. So the other side of the Bellman equation, the second equation, tells you Q pi star in terms of V pi star. And it says take all the possible things that could happen on the action you chose and sum up the probabilities. And you can either go up by 2, by 3, by 4, or by 5, or by 6. And that all happens with 0, or they all happen with chance 1/6. So Q pi star is this sum of V pi stars. V pi star is the maximum of S and Q pi star. So very nice equations you can solve. I'm going to now do a substitution to put it in the computer. I'm going to take this Q pi star and I'm going to feed it in here. So it's going to look like this. So plug. All right, let's give them names. This is the funnest thing about math, is giving your equations cool names. I'm going to call this equation dagger. This is equation dagger. And this equation double dagger. All right, double dagger. Okay, substitute substitute double dagger into dagger. And what do you get? You get this nice equation, v pi star of s. It's the maximum of s and 1 over 6 v pi star of s plus 2 plus dot 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 plus 1 over 6 v pi star of s plus 6. So I don't know what the optimal policy is, but I know that it must satisfy this. It must satisfy this equation. And so now the question is, can I cook up a scheme on my computer to solve this equation? Because once I solve it, then hopefully we'll have the answer. We'll know what the pi star is. So this is the Bellman equation for this thing in terms of v, in terms of the value function v, having eliminated the quality functions q, and now we try to solve it. Try to solve. Okay. And there are very many different ways you can try to solve this kind of thing. The most simple one is something called value iteration. Value iteration. And that's the one I'm going to show you first. Value iteration. And in value iteration, what you do is if you have some equation that you want to solve, you just keep plugging it into itself over and over again. I'll give you the simplest possible explanation of value iteration. Imagine you want to solve cosine of x equals x. Let's write it as x equals cosine of x. So here's your question for you. X equals cosine of x. I should have brought a calculator for this. How do you solve x equals cosine of x? You're holding a calculator. Is that your phone? Okay, you have a calculator. Okay, you're going to be my subject demonstrator. Here's how we're going to solve x equals cosine of x. Type in any number.
5.
Okay, great. Now hit cosine. What does it say?
Well, and I have to hit cosine 5.
Yeah.
Yeah, okay. 0.99619.
Okay, now hit cosine again.
0.999848885.
Now hit cosine again.
0.999847774.
Wait, okay, hold on. It didn't change very much. Right? Now hit cosine one more time. Hold on.
0.99984.
Okay, great. So it's look, he had this number. We hit cosine. We got the same number again. We found the solution to x equals cosine of x. It's the number 0.99984. Now I have no idea if you're in radians or degrees. So it's,
I think I am in degrees actually.
okay, yeah, this is not the answer I expected. I think you're in degrees. Okay, but the point is, if you want to solve an equation like x equals cosine of x, a valid way to try to do it, and it won't always work, but a valid way to do it is just hit the cosine button on your calculator over and over and over again. And the number you get eventually, if it doesn't change, then it's a number where when you hit cosine, it doesn't change, and then x equals cosine of x. And mathematically, what we're doing is we're making a sequence. You're doing x2 is the cosine of x1, and x3 is the cosine of x2, and x4 is the cosine of x3. And we pray, we go to the math gods and we say, please can we make sure that the sequence converges? Because if this sequence converges, right, if the limit as n goes to infinity of xn exists, then it will satisfy, let's call that x equals cosine of x. Right? So the sequence represents what happens if you apply cosine to it one more time. And if that limit exists, well, then you apply cosine to it one more time and you haven't gone anywhere. You've gone one term further in the sequence, but that's what you converge to. Okay, I will leave this as an exercise if you want to prove it. I'm going to put it in the computer now because we have exactly this type of equation over here. V pi star equals some crazy operation involving s's and maxes and things in V star. So we're just going to take this right-hand side. We're going to think of it as an operator, and we're going to make a sequence of v's, and we're going to pray to the math gods that it converges, okay? So we're going to, our strategy, we're going to make a sequence, v1, which will be, we'll initialize some v1. So initialize v1. And then we're going to, v2 equals the maximum of s. And then we're going to do this thing, 1 over 6 v1 s plus 2 plus dot 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 plus 1 over 6 v1 of s plus 6. Okay. So in other words, V2 is obtained from V1 by applying the right-hand side of the Bellman equation. And then we're going to make a V3. V3 will be obtained from V2 by applying the Bellman equation. Okay, and so on. I guess maybe I can make that a K. Let's replace the these with K's and K plus ones. So we'll make it, if you want to do VK over here, that gives you VK plus 1. So we're going to have a sequence of value functions, and if we're lucky, they will converge to something, and that something will be the optimal value function, V pi star. That's called value iteration, and it really is just like iterating a function over and over again on your calculator. Let's see it in action. Okay. So here we go. This is the code that does it. Value iteration. Here is the equation we want to solve. Okay, I guess you can't zoom in by doing that. Okay. So that's the equation we want to solve. This is the iteration. I guess I wrote it as a superscript over here. Okay. So here we go. Here's how I'm going to do it. So let me explain the code to you. So I set some number of iterations. I guess I also have to make an n max. N max. Let's make that 50. Will this run now? Okay, great. Okay. Spoiler, it runs. Okay. So here's my code. Let me zoom in and explain to you. So I made one thing called V. But I promised you there's supposed to be a V1, a V2, a V3. Where's the V1, V2, V3? Well, V actually has two things. It has a num iters, which is its first entry, and then it has n max plus 1. So it's like an array, a two-dimensional array, where every row I'm thinking is a new thing. So the first row is V0, the second thing is V1, and I even initialize V0 to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Right? That's the np.a range. So V0 is my initial guess. That was this line of the code. I guess I called it V0. Let's change it to a 0. V0. And I'm making it V0 of s equals s. That's how I started it on the computer. Okay, great. And then for every k in the number of iterations, so num iters is the number of iterations I'm doing, how many times did I press cosine on my calculator? It's going to be num iters. For every k, here's what I'm doing. First, I'm going to print out the first couple of values of v so we can see what's going on. And here is a nice little trick. This looks a lot like the equation that we had, right? On the computer, unfortunately, you can't just do ... You have to actually type everything out. But this is the equation, right? V of x plus 2, v of x plus 3, v of x plus 4, v of x plus 5, v of x plus 6. And then here is the maximum with x. So this should remind you, this should look exactly like this equation over here. I guess over here I wrote it with an s, and over here I wrote it with an x. But they look very similar. So it really looks like a mathematical equation. And this is a nice trick. There's a NumPy command called np.indices. And np.indices will let you, when you do an equation like this, run it for all the x values at once. So instead of just saying like a for loop, x equals 0, x equals 1, x equals 2, by putting x equals np.indices of the size of the thing that I want to do, it does all of them all at once. So this is like a shortcut. You could have written it with a for loop. It would have been the same thing. But there you go, the maximum of all those things. And then I just do it again, right? It's a for loop. So it runs num iters times over and over again. And then I plotted a picture of them. Questions about the code before I show the plot? Okay, let's see the plot. So here it is. And here are the values. So V0 starts at 0, 1, 2, 3, 4. So our initial guess was that if you're at state 0, you get $0, which is of course wrong, right? If you're at state 0, you can do better than getting $0 because you can choose to roll the dice and do a little bit better. And actually, after one iteration, we think the value of state 0 is 3.3. That's because 3.333 happens to be the average value you get after one roll. So 2 plus 3 plus 4 plus 5 plus 6 divided by 6 is 3.333. So after one roll, we're like, wait, geez, you don't need to just get $0 for starting at 0. You can get $3.33. You choose to roll again. And actually, you can do a little bit better than 3.33 because wherever you are, you can choose to roll again and again. And then your value goes up a little bit more. You're like, whoa, look at all this value we can get. And it keeps going up, up, up. And you see it converges. These numbers are increasing for a while, increasing, until V8 and V9, they start to get very close together. After V9, we've only gone up in the 4th decimal place or something. And then at V10, we go up by a tiny bit and V10 and V11, literally no change. So after V11, it looks like it's settled down. We found a solution to the equation. We're hitting cosine on our calculator, and nothing is changing. Let's see the plot. And here's what it looks like. So we started out at V0 was a line. The value of state 0 was 0. And then as you apply this thing more and more, it goes up, up, up. But it kind of slows down, and it reaches a steady state. We found a solution to the Bellman equation. And that last one, V11, is the optimal value function, V star. So we found V star. And we know in this case we got lucky. It worked. The computer is literally not doing anything. The thing it spit out after 11 iterations is the exact right answer. It satisfies the Bellman equation, and it will be the optimal value function. In other situations, you might not get as lucky. You might not converge exactly. You might just be getting closer and closer to something. But in this case, it worked perfectly. Yeah?
So this tells us what the value function for the optimal strategy is.
This tells you the value function for the optimal strategy. So pi star is the optimal strategy. Let's see. So V pi star. So this is not just the value function for a strategy. This is the value function for the optimal strategy. Yeah, this is a great point. And that's why it's the maximum, right? So it's doing the maximum. Okay. So great, we did it. We sort of, like, in some sense, we checked all the possible strategies all at once, right? And we found the optimal one, which seems pretty wild to me. We went from 2 to the n possible strategies, but by doing it in this clever way, we were able to check them in a way where we could check them sort of all. We found the optimal one without having to go through every single one. Question for you guys. This is V pi star. How do you figure out from V pi star? This is the optimal function, and this is telling you, for example, if someone is like, we're playing this as a casino game, how much would you pay to play the game? You could pay $8.14, and it would be break even for you. But the question is, when do you choose to roll again, and when do you choose to stop? So that information, where is it hiding in here? So this is V pi star, the value of the optimal strategy. But if you're actually playing the game, you need to know, when do I stop? When do I roll again? And it's in there. So I'll give you 1 minute to think. Where is it here? So if you find the best value function V star, in the book they call V pi star, V star, how do we determine which action is the best? How do you find A star? Okay, and I'll let you think for a minute. It's not so hard. Okay, let's do 2 minutes of this, and then I'll tell you the answer, and then we'll call it a day. Okay, and I can put the thing back. If you want to think about where it is.
Rates your current position. Right? So if you look at the current index, if you look at the index corresponding to the current position, it gives you the value of that position. Right? So if you the first position decreasing
Okay, there's like 30 seconds left. It's okay if you don't have an answer, but if you think you know it, put it in, and we'll see if you're right. I guess you have to find a clever way to describe it in like 2 words.
Yeah.
You could just give me the first couple verbs of what you're going to do. All right. Let's see what people think. Okay. No more beeping. Okay. I'm very cool. Okay. The numbers that sequence converges to, matrix. Get, oh, this is great. See, this is not the word get Q. This is get Q of SA using the value function. This is exactly right. Okay, let me see what else people said. Guess, great, guess. Pick max, first decreasing, max value, other values converge. I don't know, man. Yeah, that's great. Where are the lines? Okay, this is the easiest to understand one. Where the lines overlap. So look at this picture. Here, the lines were increasing, right? We were like learning, you can do better and better and better. But up here, it was all overlapped. And that is showing you that the value function we found is just the function s. So up here, v pi star of s equals s, which is what we started with, right? We started with this guess. We said, let's start with this guess. V0 is s. And for these large values, high values, v pi star, the optimal thing is still s, right? And that's saying that if you're playing and you get to 50, you need to stop. Just stop. Like your value of what you are is where you are now. Do not roll again. Over here, the value is larger than what you have, right? So if you're at like 3, the value is larger than 3. That's because you can choose to roll again. On average, you're going to get more points by rolling again. So in this one, where you're larger than s, that's rolling again. Where here, where the lines overlap, as the person said, you stop, because the value is s. And in general, the actual really simple thing, if you look at the Bellman equation, it had 2 parts, right? The Bellman equation said the maximum of s or this stuff. And these 2 things, they weren't just things, they represented what was going on. They came from the Q values. Yeah, look, here they are up here, where they came from. Here is the maximum of s and the Q values. And if you're equal to this part, that means stopping is the optimal thing. If you're equal to this part, that means rolling again is the optimal thing. So take the value function, look at where is it choosing to do this one, where is it choosing to do that one, and that will tell you if stopping is optimal or rolling again is optimal. A very simple way to do that, you can ask the computer to please explicitly calculate the Q functions. So I calculated V. You can get Q from V by this equation. Look at this nice equation. If you know V star, you can figure out Q star. And that is what I asked it to do over here. And hopefully this will make it very obvious what's going on. Oh no, it didn't run. Why didn't it run? Okay, will this one run? Okay, here we go. So here it computed Q. Q staying is always the dotted line. You always get S points. If you choose to roll again, rolling again is better than staying if you're here. Rolling again is worse than staying if you're up here, right? So this tells you where to do what. You just look at the different Q values, and that will work as well. Okay, stop there. If you want to come to the colloquium, I'll see you guys at like 11:30. There's some snacks and things. Otherwise, see you on Thursday.